In fact, some of nature's most ingenious tricks depend on surface structures built on a really tiny scale, far smaller than a human hair. The iridescent color of this butterfly comes from the way light scatters across the textured surface of its wing, not because of any pigment. This lotus leaf is self-cleaning, thanks to tiny needle-like protrusions that repel water. The droplets roll off the leaf, taking the dirt with them. And this desert beetle has tiny bumps on its back that collect moisture from the air until just the right breeze blows the droplets down to its mouth. In each case, nature has come up with something new just by manipulating the surface of a material on a very small scale. Now, scientists are trying to do the same thing to create new powers, maybe even superpowers. Like Spiderman. Now, in case you aren't that familiar with Spidey, he depends on tiny structures, little hooks on the tips of his fingers that let him climb walls. Can we create a material, a smart adhesive, that will let us do the same? Turns out the best bet for that doesn't come from a spider, but from another natural wonder, the gecko. It has a nearly limitless ability to climb. The weird part is that gecko feet don't feel sticky to the touch at all. Yet somehow they stick and then unstick with ease, up to 15 times a second. Now imagine if a human could do that. But first we need to figure out the gecko's secret. Kellar Autumn from Lewis and Clark College in Portland, Oregon, did just that. He found the answer in the sheer number and design of the hairs on the gecko's feet.
Geckos have millions of microscopic hairs on their toes. Of course, we can't see this with our naked eye because each hair is only 1/10 the size of a human hair. And each of those hairs branch down to billions of little split ends. And they can make such close contact with the surface that weak intermolecular forces can begin to add up to something really strong.
Turns out, geckos exploit something called the van der Waals force. If you think of an atom as a dancing couple, when you bring two atoms into very close contact, part of one atom can get attracted to part of the other. That very weak bond is the van der Waals force, and it sticks atoms together. Proximity is the key, but bringing two materials that near each other is harder than you'd think.
When I put my hand on this table, I have an apparent contact area, which is just the surface area of my hand. But the true contact area is probably a 10,000th of that. The surface of my hand is like a molecular mountain range coming down on a desert landscape. So only the tips of your molecules ever interact with the surface.
But when a gecko places its foot against a wall, all those branching hairs are like a forest pressed against a desert. And when the gecko climbs, it drags its foot down, bringing not just the tips, but the sides of all those hairs against the surface. With up to half the area of the gecko's foot in close contact with the wall, the van der Waals forces really add up. And we can measure just how powerful all that gecko hair can be.
What we measured really surprised us because the force was so large that a gecko's worth of hair stuck at once could lift about 250 pounds.
That's a lot of stick in a very little package. But it unsticks just as easily when the gecko peels its toes off the surface.
This is an adhesive that's sticky when and where the gecko wants it to be, but it's actually not sticky the rest of the time. A smart adhesive.
You know what? It just asked me if I want to save 15% or more on my car insurance.
So now that we understand gecko adhesion, can scientists match it? I head over to Stanford in Palo Alto, California, to visit Mark Kutkoski, who's building a climbing robot based on Gecko principles.
Our motivation is that we want robots to go anywhere. So we've had robots that can run along the ground for some time. The unmet challenge was to get robots that could go on vertical surfaces, especially smooth ones.
Imagine a world where robots could climb anywhere. Everything from everyday tasks like window washing to specialized ones like emergency rescue or surveillance would change. The key Gecko feature on this robot is the material used for the pads on its feet. They're made from silicone rubber. Tiny wedges on the upper surface of the pad use the same Gecko principle of directional adhesion, adhering when dragged down because of the close contact, but the rest of the time not sticky.
This is one pad on a little suspension with a weight about 200 grams below. If you just touch it to the surface, it's not sticky at all, but if you let
Not at all.
let the weight hold it,
Oh man.
sticks perfectly.
So
And now
the
to
weight
get-
is pulling down. That's the directional thing you're talking
Exactly. And then to get it off, you actually have to remove the weight, and then it will lift right off.
about. So it's quite firm now, but if I lift up, oh my gosh, it's like
Pops
the
right
electricity
off.
was turned off.
That's directional.
And that's what the real Gecko does.
And that's what the Gecko does. And in fact, if you've ever seen a Gecko going head first down a wall, you'll see that it's turned its rear feet backwards. And it has to, otherwise it wouldn't stick.
Time to see the Gecko in action. The lab's most recent creation, StickyBot 3.
And this is a ground granite slab, like a kitchen countertop. So
Okay.
it's too smooth to use something like little hooks or spines. So we really have to rely on the adhesion.
Start the Gecko! Pretty impressive. And especially when they show me a piece that supports 45 pounds. I start having my own ideas. If I had gloves made of this stuff, plus socks, could I not make myself a Gecko costume that would let me climb walls?
You're not designed to be a Gecko. You'll get tired, but you should stick.
They say Gecko adhesives would be useful anywhere you need extra grippiness, you know, tires or surgical bandages or sports equipment. But come on, we all know the real reason to develop Gecko adhesives, so you can do this!